This was for some years ago, but not so many, only few, I mean, and was the PhD students before the last one, so it is not much. But they change a lot, so maybe this looks old. But you see the details of these kind of simulators. There are probably many, I'm not an expert of this. And you see here, these are the controllers. I don't know if it is working. Yes, the controllers, so the PV, the photovoltaic units that have these agent controllers here. There is the antenna of the, and this is the communication in the network. And this is what is implemented inside of each unit with the layers of the communication network. And these are the rules for this exchange of the phasors between the two units. And these are the images of the packets that are going around. You see the packet that is spread by the antenna and then exchange. And when there is one of these that is this, that is involved, you see the packet that goes around. And so with this detail, we can say how many packets reaches the other, no? So the receiver or not, or blocked or delayed, or there is this latency that is the delay in this communication. Good, the last part. It is still running. So the last part of the lecture it is focused on the parking lot and the use of them for the distribution system operator. So the idea is that the parking lot with many charging stations may be flexible in the consumption. So they have a profile of consumption, but if there is a parking lot of an airport or a train station or a commercial center, no? The people that are arriving, probably they connect, or we assume, I don't know, in the future we connect the electric vehicles to the charging station, then they go, and the car can stay there for a long time. We have not considered several days. We have considered just that at the beginning, at the end of the day, the parking lot is empty, no? And just the car are parked and connected to the charging station for a while, no? For some hours and so on. So we have not considered here a very powerful charging stations, fast charging and so on, because the people are going there just charge for a few hours and then because they are doing other things, I don't know, the commercial center and so on. Good. So since the cars are connected, they have their battery, so it is not needed that they are charged very fast at the beginning, but they can also charge a little bit less at the beginning and more at the end, or vice versa. So there is somehow a flexibility because there is a storage. So this flexibility we assume that it is a parking lot with several tens of these charging stations, so this flexibility can be offered to the distribution system operator. So you see here the parking lot with the electric vehicle parking lot is the cars, and a coordinator of the parking lot, a manager, that can offer some a reference profile and also flexibility margins in up and down to the distribution system operator. So we can assume that the distribution system operator can use these flexibility margins to perform on optimization, in particular a voltage optimization into the network. So use these parking lots in order to improve the voltage into the network. We assume that the distribution system operator is focused on the voltage. We have this idea. and therefore the distribution system operator gives some orders to the parking lot to reduce or increase the power with respect to the reference value in agreement with the margins, so the feasibility margins, and also we expect that the distribution system operators provide some money back to the parking lot, so remuneration, some reward, financial reward for the provision of the reactive power service. Is it a scheme that it is realistic in the future, but it can be, no? No, can be. And it is this market of flexibility. So the idea, the scheme of the procedure, power flexibility, so we have a reduction, and here, probably here you cannot see, but here you can see this part in green. So the idea is that if we reduce always the power of the parking lot cannot charge the cars. So the parking lot receive a remuneration from the DSO, but the people that are using that parking lot for the charging station, they are not very happy because they don't charge their cars. So we assume that the cars are taking the same service, but they can take without this flexibility. So the maximum charge compatible with the timing that they stay there. No? So if we decrease the power in one period, then, or in some periods, then we need also to recover the power because the total energy is the same without and with the flexibility. Is good? So there is this idea of this recovery period. And then the second figure, it is the voltage optimization by the DSO that use this capability, power flexibility. And at the end, I will try to show also a test case. Any questions so far? For the terminology that I have in this, we said that the parking lot is PL. So when you read the PL, is a parking lot. And then the network, the voltage optimization is some kind, simplified, so that we don't take into account the voltages in every bus, but voltage only in some buses that are considered to be representative of all the system. So they are, and so these are the pilot voltage control zones and the pilot bus that are in the areas of the network. Here there are 3 areas, and so for each area it is identified a specific bus, so that if we optimize the voltage there, we have optimized the voltage more or less in all the other buses. So use the flexible operation of electric vehicles, parking lots for optimization of the voltage profile in distribution network. We have implemented 2 things. One, it is a day-ahead stochastic optimization. Why stochastic? Because we don't know in the day before how many cars will come and when and what are the characteristics. So in order to take into account the uncertainty, we developed a day-ahead stochastic optimization for day-ahead for the calculation of the reference profiles and also the margins. I will speak about this. And then the flexibility provided by the parking lot is exploited by a distributed linear programming model for the voltage optimization of the medium voltage feeder. This is the DSO problem, the DSO model. DSO means distribution system operator, the people. So the overall methodology is in this way. You see here the time, the day before, and then the day is divided in some stages, so we can update the decisions taken in the day before in some times during the day. We have considered 4 stages, so at each 6 hours you can update the decisions taken in the day before. And at the beginning of each stage, so at each interval of 6 hours, we calculate the margins, and then with a time discretization of 15 minutes, the DSO, the problem of the DSO is operated for each 15 minutes in order to use the flexibility. So we speak about stochastic optimization for the problem of each parking lot, based on the scenarios, stochastic scenarios, and we speak about the multi-period voltage optimization problem. And then there is the real-time control that we have not implemented, that is the fact that in the parking lots they decrease or increase the power according to the decisions of the optimization of the DSO, so in the implementation. Multi-stage stochastic optimization, it is based on scenarios, so from the forecast of the number of vehicles that are arriving or departing or exiting the parking lot, we create several scenarios. In particular, we have created 60 scenarios, but repeating the optimization for 60 scenarios, it is too much from the computational point of view. So in order to reduce the computational point of view, the similar scenarios are grouped. So the scenarios, similar scenarios are grouped by means of a procedure that is called K-medoid. What is the difference between K-means and K-medoid? Is that K-means takes the means between the scenarios that are grouped. The K-medoid take one of the original scenario, so takes the scenario that has the lowest distance, Euclidean distance, over the other scenarios. So the most representative scenario in the group. And why we do this? Because the number of cars that are parked needs to be an integer number, cannot be 1 car and a half. And if you do an average, you take also these results, no? So you have the number that is not integer, so it is not realistic. And moreover, the number of cars in the parking lot cannot be negative, so you cannot have more cars that are exited than they are entering. So in order to take into account all these simple, stupid considerations that has feasibility, in order to be sure, we take one of the initial scenarios that are created, take into account all these. So they are not changed by the K-medoid, the grouping, the aggregation procedure. Okay, good. I mentioned to you that we wanted to be able to have some flexible decision during the day, because probably what I can forecast now about the number of cars and when the cars are coming in my parking lot tomorrow, it is not so good. So we take this flexibility so that at some instance during the day we can also change, adapt our decisions to the actual number of cars that are in the parking lot, if the car is full or not. I mean, it is different. So you see that there is this tree in which at the beginning you have just one scenario, but then 3 and then many. So we have chosen this tree because we have seen also that if you have a group of scenarios and you divide in three groups, it is enough in order to represent somehow the population of the scenarios. But in some cases you need also to increase or a little bit decrease. But 3 decisions. I think that I've said it also all. Obviously, these are the scenarios, the representative scenarios that are also associated with a probability. No? So a probability according to the number of scenarios that are grouped by this centroid or medoid in this framework. So the optimization is for the calculation of the reference profile and also for the calculation of the up and down flexibility margins for each duration of the flexibility, because the flexibility we have considered that can be 15 minutes, so we have, for example, a reduction of power for 50 minutes, but we can also think about 30 minutes, and obviously the flexibility will be different. Probably the reduction of power will be lower, and or we have considered 45 minutes. So these are the 3 intervals in which we can have flexibility, and we need to calculate distinct flexibility margins for each of them. It's good. So this is done by repeated optimization for each time. But it is the first one is stochastic. The second one is deterministic, because we are all in the stage. So this is the objective function of the stochastic. You see this pi is the probability of the scenario. The scenario is indicated here as omega. So omega is the scenario, pi omega is the probability for each scenario. We need to sum up the results for all the scenarios, and this is the objective function for each scenario, that is the summation in time of the cost of having the energy in order to charge the electric vehicles. This rho, it is the price of the energy, is euro per kilowatt hour, and this is the energy for the time period, and we have considered discretization of 15 minutes. You see that there is another cost that is a little bit subtle, because I would like to show here. Okay, you can have the situation in which the grid charges your vehicle, but in some manufacturer also they provide charging stations that are bi-directional. So we thought about how to use this bi-directional charges. And we have not found here a good reason to inject power to the network, because probably also the system operator is does not agree that you are injecting power to the network. You are not a generator, and so on. And so the good reason in order to install this bi-directional charge is that you may have some cars, some vehicles that are parked for a long time, and other vehicles that are coming and are leaving in a short time. So the manager of the parking lot may also decide to take some energy from the parked cars or vehicles, and in order to charge the vehicles that are needed to run away very, very fast. So in order as a, let's say, a backup of energy, a storage of energy for the vehicles that needs to go away abruptly. I don't know, because they have received a phone call. No? So this is and this is called vehicle to vehicle. This is not a vehicle to grid. We are not injecting power to. We are exchanging power from the. But perhaps these cars needs to be remunerated. They want some discount, or and so on, because they provide this service, because probably also the battery, they can suffer from this charge and discharge and so on. So we have considered here in the optimization, it is here the objective function, also this CS, that is the cost of using the initial energy in the vehicle and for the vehicle to vehicle service. Yeah. Is it reasonable?
The previous slide, sir.
Yeah, we were back. Yeah,
bidirectional vehicle, no? V2V.
Pardon me?
V2V.
It is this one.
No, not this one. Sir. Bidirectional charging. Cars you have shown.
Where?
No, next.
Next. It is this.
No, sir.
After.
Two vehicles you have shown. Bidirectional charging.
Yes. Yeah. This.
Actually, what is the need of using a stationed car or vehicle for using this charging? Why we actually need that one?
We don't need, but perhaps can be useful. We think about this bi-directional charge because in general they say vehicle to grid, but there is not a good, reason to inject power to the grid. Because the grid is not expected that you are injecting power if you are a parking lot.
And whatever the power we inject to the grid through this parked vehicle,
so
it is very, very low.
Yeah, so perhaps can be useful in order to say, okay, we have some limitation here, the transformer is limited and so on, and there are some cars that are needed to go away. So we can think that we cannot take many power because this needs to run away. So we need to charge at full power for that. So perhaps we can use the energy in the car in order to charge the car that wants to run away very easy.
Something like a power backup?
Yes, instead of having the battery. And probably in big parking lots, the parking lots may have also the battery in order to fast charge some cars. But big parking lots may use the already parked cars in order to charge also the vehicles that needs some fast charge at that moment. Obviously, this has behind the idea that you have not dimension the interconnection to the grid with the full total power of all the charging stations and their maximum capability. Probably this is reduced in order to limit the cost.
Speed up the charging?
Yeah.
For fastening the charging.
Yeah, because probably the parking lots are not always occupied, so probably the connection to the network is not the total one, but takes into account some reduction. No? But in this way, you can compensate for this. Is it reasonable? No? This was the scenario that we have in mind. So it is more vehicle to vehicle rather than vehicle to grid. No? It is. Here I have also indicated the calculation, no, for the flexibility margins in which there is this reward, that is the reward that is given by the DSO to the parking lot because it provides some margin, down margin, so you reduce the power with respect to the reference power, or up margin, so you can increase the power with respect to the reference margin. We have taken into account also the recovery, so this is the idea. And this is the generation of the scenarios with a forecast, many scenarios, and the grouping that we have already described before. And then this is the objective function that we have already described now. It is this one, and then this is the idea behind this vehicle to vehicle. This is the equation. There are the constraints, so the balance, the level of energy stored in all the cars. We have not considered the cars as one by one, because otherwise the number of variables are exploding with many cars. So we have grouped together. So this is the total level. So it is like a battery with a dimension that is shrinked when there are a few cars, and it is enlarged when there are many cars. So it is something like this. And the inputs in this battery, it is not only the energy that is coming from the grid, but there is also the energy that it is at time zero, no? When they connect already in the battery. So we have considered the net, and here are the losses in the vehicle-to-vehicle exchanges, and this is the use of the initial charge. And obviously, the energy also not only enters in this battery, but also leaves when the cars are leaving. When a car leaves, takes out also the energy of its battery. So it is considered here. So it is minus this energy when the car is leaving. For the calculation of these losses and so on, we need to estimate a little bit these vehicle-to-vehicle charging, but since we are not representing each vehicle separately, we just compare the profile with the total energy that is needed in order to charge that vehicle. If that vehicle is charged more, it means that it is involved in a vehicle-to-vehicle charge because it has given some charge to the others. If a vehicle is charged less, it means that it has received some energy from other vehicles in the vehicle-to-vehicle. So with this comparison, we have the total amount of energy that is changed in the vehicle-to-vehicle transactions, and so we can associate to this energy also a price, a cost, no? So we can include this cost, and also we can say that part of this energy will be lost. And in order to simplify the thing, we have considered a fixed efficiency for the converters. So not depending on the load, but the power converter of the charging station, they have just an efficiency that is fixed. This is the model. All these equations, and then this is multiple step flexibility calculation. So there are these rewards that I already mentioned. These are the revenues for providing up and down margins, and this is the idea that when you have, for example, a flexibility down, you need to recover after. So there is a period that we have fixed in 45 minutes after the provision of the flexibility, in which you are allowed to recover, so to, for example, increase the power, in order to recover the service of the charging to the. So it is not a battery. It is something that has many limitations with respect to the battery if we want that the cars are fully charged. No? Otherwise, there is a decrease of the service, of the quality of service of the charge. No? Do you have any questions so far? Is it reasonable? So the case study that we have considered are these. So you see that the number of charging stations is quite high, no? 77, 45, 210, and so on, in order to see if this method can deal with large parking lots with many charging stations. So these are the type of cars that we are expecting, because it is a stochastic procedure, so random, taking into account the penetration. I don't know if they are reasonable, but I mean, we have taken from internet these values, but they always change. No? In particular, most of the cars here are between 40 and 50 kilowatt hour, no? The size of the battery. So we have taken 45 in the middle, between 40 and 50. And the resolution is 15 minutes for 24 hours. And then this is the scenario 3, an example for parking lot A. Yeah. It is the penetration because we need to create the scenarios, but we don't know which car tomorrow will connect to the distribution network. So it is a scenario that is randomized. So the cars that are, the vehicles that are coming, we probably we say, okay, we forecast that there will be 10 vehicles that are at noon are connecting to our substation. Of these 10 cars, what type of cars are there? So the type of cars is defined by this table. So there is 45% of probability that there are cars with this size of battery, and there are 15% of probability that the size of it. So in order to estimate the type of car, we don't know. We cannot, I mean, it is, I don't know, probably people that are doing forecast, they can correct me, but I think that is difficult to forecast also the type of car or the color. I don't know. But it is simple to have a forecast of the number, because probably at the entrance of the parking lot they take a ticket, and so they have an history of how many cars are parked in all the days before, and so on, from the history, and so they can imagine also how many cars will be connected tomorrow, taking into account the history, and also that tomorrow will be Friday or Saturday or Sunday, and so on. Is it good, correct? Yes. Yeah, maybe. So the idea is this. So in this way we have created all these scenarios and just combined with this. So you see that instead of having all these 60 scenarios, the number of scenarios is reduced. So it's just 3 times 4. And it is multiplied. No? So it is 27, I think, scenario at the end, because some are grouped together. I don't know if they are all 3. Because, for example, these are 2 only because they are very similar. One was very similar to the other, so was grouped together. So these are the scenarios, I mean the profiles for the parking lots, the forecasts, entering and leaving, the number of cars that enter and leave in all the periods, and this is the number of parked electric vehicles that is, is combined. This is obtained from this for the different parking lots. We say A, B, and C. Okay, the last one is double the A. So you see different profiles. Okay, so these are the calculation on up and down margin variation. This is just an example. You see the number of periods, and you see here the flexibility down and flexibility up for a parking lot with respect to the reference profile. And this is a table that describes when there is the flexibility. You see that the flexibility, there is, this is 23. These are the periods. So before 23, there is no flexibility because there are no cars. So you cannot have a flexibility when the parking lot is empty. So at the end, at the beginning of the day, there is no flexibility in this simulation because we expected that the parking lot is I don't know, closed. So we fixed that the number of cars at the beginning and the end, it is 0. And by assumption. It is an assumption. And these colors indicates when there is the flexibility. The first period, so the first row, it is just for 1 period flexibility, 2 period flexibility, 3 period flexibility. The green is down, the red is up. This is 2. There are periods, for example this, in which the same parking lot can provide both flexibility up and flexibility down. And so there are 2 colors. This data, with also the indication of how much flexibility, is given to the distribution system operator. So the distribution system operator, we are running, no, we have some time, no, it is given to the distribution system operator. So the distribution system operator can carry out the voltage optimization. So this is the problem for the voltage optimization in the distribution network at the beginning of each stage. So every 6 hours, the parking lot, we are expected to provide this flexibility. So the parking lot does not provide the flexibility the day ahead before for the entire day, but just for every 6 hours. This appears to be more reasonable because giving all this data just the day before was, was risky, no? Because they don't know. Every 6 hours, probably. It cannot give the indication every 15 minutes because it is difficult for the distribution system operator to do all this work in so. So we thought, oh, every 6 hours, the parking lot gives this flexibility margin to the distribution system operator. The distribution system operator calculates how to use it and if using them. So there is an objective function that we have take into account this voltage problem. So you see that it is the minimization of the voltage deviations with respect to the reference value. The square is due to the fact that, we wanted to minimize both deviation up and deviation down. So the sign is taken out. Indeed, this, it is a rolling optimization for every hour. So every hour it is a rolling horizon of 1 hour that is going with a 15 minutes step. So the optimization in 1 hour, we take the decision for the first 15 minutes, we repeat the simulation again for 1 hour, and we take the decision for the 15 minutes, and so on, so on, so on. So it is in this way. For all the day. So this vector can be defined in this way, so the voltages and also the reference. So the objective functions can be rewritten in this way. So you see that here there is one summation only. Here there are two summations, one for each recovering period and one for each node in which we control the voltage. We said that we don't control the voltage in all the buses, but just in the representative buses, so in the pilot buses. And there are two summations, and here there is just one summation because the other is just the product of these two vectors. It is a row to column operation. Then the control variables are X we may have some flexibility from distributed energy resources, and then flex up and flex down for the parking lot. So these are the three. These for the distributed energy resource can be positive, active power and reactive power. For the parking lot, we assume that it is just active power because we assume that the charging station operate a power factor close to 1 or they are fully compensated. But I don't know. I'm not aware of a manufacturer of charging stations that are varying the reactive power. Probably it is too much. No? It's good. We can just decrease or increase the charging. Oh, if it is good, this is also includes the representation of the power flow equation. It is a linear representation, and the constraints are relevant to the energy recovery in the parking lot. So the same constraints of the parking lot are replicated here in order to, not all the details of the parking lot, just to recover all the energy that is provided in the flexibility period during the recovery period. So we can maintain the same quality of service for the charging stations.
For this,
yeah.
Whether we have to use MATLAB programming?
Yes, this is implemented in MATLAB. Yes, this part for the optimization of the network. For the multi-stage stochastic programming, we are using a software that is free for academics. That it is just, I don't know why we are using, probably it is free because we have already used, so it is called IMS. But it is just an interface between your model, no? So you write the model in IMS that has a nice interface, so I can understand also. We can also understand each other when one has done something, the other, because it is. And the solver. So the solver is Ciplex or Gurobi that are also, and these solver are also coming from IMS. So if you are in a university and so on, you can apply for the academic license and so on. But it is not an advertisement, and I don't know why we are using this. We have started in some work, so you can replicate some part of the thing and so on. And the main reason is that it's free. So then, it is also, adequate for the purpose. So we can implement this. A case study. This is the 123 bus, the network, the IEEE system, and it is a network that is a medium voltage, but not so high voltage. It is 4 something kilovolt. So also the size of the parking lots needs to be, so we have not considered here the big parking lot with 210 cars, because probably cannot be connected in that network. We have only chosen the others. And the other types are 4 control zones for the voltage. So you see here there is this, and there is this one, and there is this one, this area here. So there are the calls, so you can identify better these. For each zone, there is a bus that is chosen as a pilot. So we control just the voltage there, not to control the voltage in all the buses. That is a representative. You see also where the parking lots are located, that they are the blue one, and they are 4 parking lots located probably in the extremities, and also there are the red that are the photovoltaic units that may also compensate a little bit for the reactive power. Here we have just indicated the minimum and maximum reactive power according to the active power during the day. Sorry.
So you also consider the optimization of all these power stations?
Yes, the optimization takes into account all the photovoltaic. No, the location is not optimized. It is just a random. We put there. Probably we put also take into account and saying, okay, probably the reviewer of the paper likes that we put the parking lot at the extremities, so in the difficult position and not near the substation. The flexibility is not used because there are no problems for the voltage. So we have connected the parking lot in points where probably there are some problems for the voltage, and they can be useful for this. No, it's good. But it is not optimized. The optimization where the parking lots are located, it is a nice subject, and there is a literature behind that, but it is the same as the sizing of these distributed generators. If you think that the distributed generators are owned by the utility, it makes sense, clearly, no? Because the utility has the problem. Oh, I want to put some distributed generation. Where to put? No? But in the Italian case, the distribution system operator cannot own any power station, anything. There are also problems to install the batteries, because also with the batteries you can play with the price and so on. So it is not the role of the distribution system operator. So the distribution system operator has no any decision on where the distributed generators are connected. It needs just to connect by law, because it needs to guarantee to everybody to connect. Obviously, there are some agreements, no? So some checks, no? So you cannot change all the circuit breaker in the network in order to connect a PV panel, no? So also for the parking lot, we think that at least in Italy, no, there is less power from the utility to say, oh, the parking lot needs to be there, because the network, it is the reverse. The parking lot is where it is needed. There is the airport, there is the commercial center, there is something, no? And there is the space. and then you need to connect also this charging station.
Places.
Yeah. So probably it is a random, and then in many cases the electricity infrastructure needs to adapt from the decision of the others, rather than force the other to follow somehow the best way to do. This is the case. So you have seen this. And these are just the data for the simulation. So this is the load photovoltaic during the day, and it is assumed here deterministic. We have just the stochastic for the parking lot, and then this is the time evolution of the objective function of the voltage optimization. So you see that the objective function is quite limited in all the hours here are included, and here there is the voltage optimization that use only the distributed energy resources, and in blue the optimization that use also the parking lot. So are the parking lot flexibility is useful, or in many cases no, but you see that in this point, oh, that is quite useful, no? Because the parking lot can allow to reduce this objective function that is the error in the voltages. So it means that in some hours it is useful. This is the voltage profile during the day. This is just the voltage in a single bus that is in the leaves node of the network. So you see here in black without any optimization, so you have some variation, not much big, but there are, substantial variation of the voltage, and then with only by using the distributed energy resources in red, and in blue, the one with also the parking lot. In some periods, you cannot optimize nothing, because the parking lot is empty. so there are no flexibility. In other periods, the use of the flexibility of the parking lot allows to reduce the voltage deviation. Is it? This is the schedule reference, and what it is said by the distribution system operator for a parking lot. This is PL2. So you see that this is the schedule and the actual. So in some cases, the schedule was higher and the actual is lower, because there is the flexibility that is used. And in some cases, there is here a strong reduction. And then you see that there is an increase after, that is the recovery. So it is reduced in this period, but is a recovery in the following 3 periods. Also here was reduced here and was increased. Now this is the opposite. It is increased here and decreased here. At the end, the same energy of the schedule is also the energy from after the optimization. There is this constraint. So this for another parking lot, I made a mistake here to say it is PL2, it is another one. And this is PL4. So you see the same behavior. Decrease in one period, and then there is a decrease, an increase in the other periods, in order to maintain the flexibility series. At the end, we have also compared this with the voltage deviation index calculated for 24 hours, sum of the objective function values through power flow calculation every 15 minutes. So we have two cases we have considered. The one that I already shown, in which case A, in which it is 200 kilowatt, the rated power of each photovoltaic system, and the other with 300 kilowatt. It is not the only difference, because in case B also the load is decreased to 30% of the initial. So case B has much more photovoltaic rather than the load. So the photovoltaic is increased and the load is decreased. And you see here that for both of the two cases, without optimization, there is some error. So this voltage deviation is quite significant. And with that, the DERS is reduced, with the parking lot is reduced again. So also the parking lot helps in this way. So in brief, the method to characterize and use the flexibility provided by the parking lots equipped with electric vehicle charging station for the optimization of the voltage profile in the distribution network, assuming a predefined reward per kilowatt of up and down flexibility service. The electric vehicles charging station calculates both the reference demand profile and the flexibility margins in advance. I said at the beginning of each stage, every 6 hours. And then for this purpose, a multi-stage stochastic procedure is implemented, allowing recovery after the period when the flexibility is requested. And then there are some also, summary for the voltage optimization, that is the flexibility margins are incorporated as a control resource in the voltage optimization procedure. The procedure decouples the networks by using the pilot nodes, and the procedure is applied to the 123 bus test feeder. And to enhance the flexibility of electric vehicles parking lot, power reduction and increases in consecutive periods can be enabled while ensuring schedule flexibility. So it is not I provide just for 15 minutes, you can also calculate the margin. We have calculated the margin also for 30 minutes, also for 45 minutes. Then we stopped because we said, okay, we are not flexibility, because for a parking lot, if you decrease the power for several hours, it is difficult to guarantee the charging of the electric vehicles. This concludes this day lecture. I don't know if you have any comment, any suggestion, question. Probably it is lunchtime time. Thank you for coming this morning. Thank you. Thank you so much.